Professor. One open list.
Yeah,
Dear colleagues, I am happy to say that today we have a guest in our laboratory, Professor Klingshirn. We know Klingshirn many years because we textbook for our students, for us all, this first edition of this book. And now Professor Klingshirn presented us fourth edition of this book. So with accumulated knowledge and accumulated experience of Professor Klingshirn. As I can guess, yes? Together, huh?
My knowledge.
So today the second lesson. I hope most of you attended the first lesson. And second lesson will be for specialists. We know what does it mean excitons, so you can just explain new physics on these excitons.
Okay.
One question: may we ask you during your lesson questions?
Sure.
Okay.
Yeah.
Thank you. Please.
Okay. So, good morning, everybody. We had the day before yesterday a lecture, and I introduced the concepts of band structure, excitons, polaritons, bi-excitons, plasma for bulk material. We did not finish completely. There was something left concerning excitons in quantum wells. Now I will now start with the second part, because the first few examples here will also concern bulk material. And when this is finished, I take the part which we missed last time, which goes into quantum wells, and then we continue to quantum wires or quantum dots and things like this. So, okay. The first will be phonons, plasmons, and surface polaritons. And before I go to part 2, I will take up this missing part from yesterday. Now that you are now the experts and you know what a phonon is, you have the interaction potential between atoms in a crystal, and you can make a parabolic approximation, and you can write down the equation of motion and solve them, and then you get, for a case that you have 2 atoms per unit cell, for a linear chain, you get such a dispersion relation, the acoustic branch, the optic branch here, a gap in between. And I was speaking the day before yesterday a little bit about Brillouin zones, and that you can map everything outside the first Brillouin zone into the first one. And this is even more obvious for phonons. If you assume that these are the positions of the atoms, the shortest physically reasonable wavelengths would be such an elongation. This is a minimum wavelength, and the maximum k-vector for a cubic lattice again pi over a. Of course you can define, if you want, in between a shorter wavelength, but it does not mean anything. So this would be something in a higher Brillouin zone, which you could shift into the first one. Now if you go to a 3-dimensional crystal, you get always 3 acoustic phonon branches, 2 transverse one and 1 longitudinal one, and then you may have so-called optic branches, and the number of the optic branches is 3n minus 3, where n is the number of atoms in the primitive unit cell. They are called optic because they couple to the radiation field, provided that they are connected with a dipole moment. They can also couple be Raman active if they modulate the polarizability, and in cubic crystals they can be either optically active or Raman active. In lower symmetries they can be both. And I show you here the normal modes for the phonons in Wurtzit structure. This is zinc oxide, gallium nitride, and so on. They are crystallizing in Wurtzit structure. And you see here a displacement of one type of ions in one direction and the other 2 in the other direction. Be careful, you have to rest here. Okay, thank you. And this is evidently a electric dipole moment. And this is an oscillation which is elongated parallel to the crystallographic z-axis, and this has symmetry gamma 1. This would be an elongation perpendicular to the z-axis which carries a dipole moment, and this is twofold degenerate because if you have the z-axis you can elongate in this direction and in that direction. And the other ones are not optically active. And these are now examples simply for the optical properties. Here for the case of cadmium sulfide. You see here the so-called stop band or Reststrahlbande where you get a reflectivity close to 100%, and you can calculate from this the refractive index. You have here the real part of the refractive index which goes down to 0 and comes then back, the imaginary part, and you can via Kromer's chromate you can also calculate the real and imaginary part of the dielectric function which is shown here.
What does it mean refractive index 0?
Refractive
index 0, what does it mean?
The refractive index 0?
Yes.
So it means a stop band, you have no propagating mode.
But in vacuum we assume that refractive index unity
is 1, yeah, but can I move it a little bit up and explain it? Oops, there was somebody before.
Just please wait.
Okay. If you have a simple Lorentz oscillator, some oscillators which couple to the radiation field, and you calculate the dielectric function, is a function of frequency. This one is better. It's a function of frequency or photon energy. You get the typical resonance behavior. It goes to plus infinity. It's a transverse eigenfrequency. It comes back from minus infinity. It starts here to static dielectric constant. It goes here to the background dielectric constant. This is a longitudinal frequency. I explained already that you can have a longitudinal mode here. Now the refractive index is just the square root of epsilon of omega, the complex refractive index. Now if you take the square root, then you get a real part of the refractive index. This starts here with square root of epsilon s, goes to infinity, but this region here where epsilon is negative goes to the imaginary part. The real part of the refractive index in this interval is 0. And then it comes back here to the square root of the background dielectric constant, something like this. And the imaginary part, which is something like kappa, the imaginary part has a singularity here, and then it comes back like this. This is the imaginary part. And I was playing with the polariton concept a little bit. If you just multiply everything with omega over c, then this is the real part of the wave vector, and this is the imaginary part of the wave vector. And if you multiply this, you get simply something like this. And then this upper branch here. And then you have the polariton.
Light velocity. Just, light velocity in this in media. Light optical light velocity.
You have a reflectivity which is given n minus n real part minus 1 square plus kappa square and n plus 1 square plus kappa square. So if this n is 0, then the reflectivity is 1. You do not get a propagating mode. You get the stopping.
Okay, thank you.
So we appreciate it. We need to. Okay. And the beamer also, yeah. Okay. So this is with a little bit of damping, the real part of n, the imaginary part of the dielectric function, the real part, real part and the imaginary part. Without damping, it would be a delta function. It's a transverse frequency. Now these are the phonon dispersion in the Brimmer zone for a hexagonal structure, which is usual for zinc oxide and for a cubic one. And you see you can, by neutron diffraction or by optical spectroscopy, you can verify all these branches. So this concept of excitons, of phonon subs as well established. Now we go one step further. We have these phonons, may couple to the electromagnetic radiation field. You will get again a polariton dispersion. And the question is now, how can you measure this polariton dispersion? And you can measure it, for example, in Raman or Brillouin scattering. And the Raman or Brillouin photons are given by the incident photons plus or minus the creation or annihilation of a phonon. And we go here, we do a backward scattering experiment. This means we shine at this frequency with a laser on the sample. This would be the exciton polariton dispersion with a resonance somewhere up there. We are looking in backward scattering, and this is now with this minus sign here, the dispersion of a phonon polariton. You have the lower polariton branch, which goes over to a phonon-like behavior, the transverse branch, the longitudinal branch, the upper branch, and here's the acoustic branches, and you see you get here an intersection, so you can observe these states at these wave vectors here. And this is Raman scattering. You see the longitudinal and the transverse. At relatively large wave vectors here, you see the transverse and longitudinal acoustic ones here. If you would go to forward scattering direction, the momentum transfer would be 0. And if you change the angle from forward scattering to backward scattering, you can scan this whole dispersion relation. And this has been done here for, I do not know what, gallium phosphide. And you see here nicely the longitudinal phonon polariton, the longitudinal branch, the upper branch. So this is verified experimentally.
For
these are the numbers given here.
Volts approximately. Rabi splitting.
No.
About 6 millielectron volts. Or maybe 5.
There are two quantities to measure the oscillator strength. One would be the transverse longitudinal splitting. This is what we usually do. This is a difference here. The Rabi splitting would be the minimum vertical distance between the upper and lower branch, which is much higher. So sometimes people are confusing these two quantities. So another new aspect, for every volume polariton mode, or for almost every, you have also a surface polariton mode. This is a mode which can propagate only along the surface or interface of two media, usually the surface between the sample and vacuum. And now the question is, why should such a surface polariton mode exist? And you must find arguments that this mode cannot decay into the bulk and it cannot decay into vacuum. And the reasons are the following. It is situated at larger k vectors than the dispersion of light in vacuum here, because the parallel component has to be conserved at the interface. If the wave vector is larger than that of the photon in vacuum, it cannot decay. It's forbidden by k conservation. And the reason why it cannot decay into the bulk is simply because it has to exist between the transverse and the longitudinal eigenfrequency, because there you have no propagating modes in the bulk. Yeah? So in this frequency interval you can look for a surface polariton mode. Of course you can calculate it a little bit more in detail. And then the question is, how can you measure it? It does not couple to the outside world, it does not couple into the space of, into the bulk of the sample. And there was a trick. This is a so-called attenuated total internal reflection. You send a light beam with a certain frequency omega into a prism under an angle that you get total internal reflection at the prism base. And we know, if you have total internal reflection, that there is a damped wave which is damped perpendicular to the surface, which propagates here along the base of the prism. Now you bring the sample under investigation very close, this means with some wavelengths approximately, to this base, and if both the parallel component and the frequency coincide with such a surface polariton state, it can couple to the surface polariton state, and then the reflectivity gets smaller than 1. This is called attenuated total reflection, and you see here some spectra for various angles of incidence. This means for various parallel k vectors. And you see here the dispersion relation of such a surface phonon polariton mode compared to theory, and there's nice.
So please, what is the surface thickness which is involved in surface polariton creation?
Order of the wavelengths. The decay, okay, if this is the interface, the surface polariton mode decays in this direction, and the field amplitude decays normal to it, and the decay distances of the order of the wavelengths.
Distance, but in infrared range. In infrared.
This is infrared range. Tomorrow,
wavelength is large.
Yeah, tomorrow you will see it also for excitons for synthesite. Yeah, for shorter, much shorter wavelengths. Yeah, this is an experimental difficulty to bring the sample so close to the prism base without touching it. Yeah. So now we come already. A first aspect of superlattices. I think you are all familiar with quantum wells. You grow two different types of materials on top of each other, and possibly this would be an occasion to switch to the rest of the other talk. And can you help me please here? No, I continue. Sorry. I continue here because this will also concern phonons. I continue a little bit in this talk. Sorry, can we go back? Yeah. Okay. Yeah. Thank you. So what you produce if you grow, for example, 10 nanometers of gallium arsenide and 10 nanometers of gallium aluminium arsenide and so on top of each other by molecular beam epitaxy, by atomic layer epitaxy, by metal-organic chemical vapor deposition or other techniques, you produce a new artificial periodicity in this direction. And this new artificial periodicity means that your first Brillouin zone gets smaller. This is shown here. Schematically, this would be the first Brillouin zone for the bulk material. Now we have a smaller Brillouin zone, and we can again fold back what is outside the first Brillouin zone into the first Brillouin zone, and you see now that even for the acoustic branch you get here states close to k equals 0, and there you can see in Raman or Brillouin scattering, it's up to you how you want to call it, and this is example from my group. This is zinc sulfide, zinc selenide superlattices. You see here these various branches, the first backfolded branches, the first, the second, the third, and you see here the calculated backfolded phonon branches for two different superlattices with different periodicity and the experimental data points, and this again fits quite well. So we have in a superlattice we have backfolded acoustic phonons. Now what happens to the optic phonons? And to the optic phonon something interesting is happening, provided that the optical phonon branches in material A and in material B do not overlap energetically. Then the following can happen. You can get phonons which are confined in material A maybe. And then you have a ground state and a first excited state and possibly a second excited state and so on. And what also could happen, that you have so-called interface phonon modes. These are modes which are now confined to the interface. If you have them, this depends on the composition, and I will show you now an example. This is a superlattice of zinc sulfide and cadmium sulfide and zinc selenide. And these are now the calculated confined phonons modes of the cadmium sulfide. Here's the first one, the second one with one node line in between, the same for the zinc selenide here. And at the interface you can get a zinc sulfide mode, and this is a frequency which is higher than all other frequencies, so it does not couple to the other phonon modes. And for different polarizations you can measure the interface phonon mode, this one here. You can measure the quantized cadmium sulfide phonons, the zinc selenide phonons.
Sorry, and how did you recognize that these interface phones?
From the frequency.
By comparison of this
From the frequency, it has, I guess also from the polarization, it has higher frequencies in all phonon modes in cadmium sulfide and all phonon modes in zinc selenide, because zinc has lower mass than the cadmium, and then the phonon mode is a little bit higher. And you can also calculate it. There are theoretical models to calculate it. If the spectral position, this dashed line, coincides with the experimentally observed, we are also sure that this is the correct assignment.
May I ask also, what was the second peak then?
This 1, 2, 3 and so on.
Zinc sulfide and zinc selenide is 240.
Yeah.
240.
240.
This one here. Okay, these two spectra are for two different polarizations.
Yeah.
Yeah. And these are the quantized optical phonon mode. So this is the first quantized phonon mode, which shows up in this polarization preferentially. This is the second one. The third one would be expected here. The fourth one would be expected here. These are these modes. The first, the second, the third would have two nodes and so on. And the same could happen in material A2. And in our case, one of the materials is...
and where is the bulk phonon here?
Beg your pardon?
Bulk phonon.
Close to 1 probably, or slightly above. For bulk zinc selenide.
The bulk would be here, this one, for k equals 0, and this is the first quantized mode, and the second quantized mode, and so on. And if you measure these modes, you can reconstruct this phonon dispersion relation. Yeah.
Yes, yes.
And this is what we do here. This is, for example, for what is it? Zinc selenide, the phonon modes over approximately 1/2 of the first Brio zone, just deduced from these quantized phonon modes.
Could it be observed also in a single quantum well, or superlattice?
No, superlattice. You need a superlattice. Yeah. Also, you have more material to scatter from.
Yeah,
multiple quantum.
But this is not physical, but really the experimental.
Yeah, sure. I was grown up with the statement, a theory is only true if you can verify it by experiments. This is why I also show the experimental confirmation. Okay, plasmons. Plasmons are collective excitations of a free carrier gas relative to the positively charged backgrounds then. And this is very old work on, what was it? I think indium antimonide. Yeah, indium antimonide. Different doping levels, different concentrations, and the plasma frequency, so longitudinal frequency, the transverse plasma frequency is 0 because the gas does not have a shear stiffness. And it goes like the square root of the density, and you see here that the carrier density was varied approximately over a factor 10. And if you look here at the longitudinal frequency, which is close to here, you get also approximately a variation of a factor square root of 10. Now, we have a polariton, the phonon polariton. It's a little bit tricky because the lower branch is 0, the transverse eigenfrequency. The longitudinal eigenfrequency is here, and we have a lot of space for surface phonon polaritons. And you can measure them. It was a little bit different than the measurement. You can calculate them, and you find again nice coincidence between the calculated and the measured surface plasmon polariton modes. In now dip, and then it drops only here. And what is shown here is now is a square root of the electron density. The plasmon mode, this would be a straight line. This is a transverse phonon, this is a longitudinal phonon. The plasmon mode and the phonon mode couple with each other, so you have again an avoided crossing. What happens, you have here a plasmon mode which bends over to become here a longitudinal mode. You have still the transverse phonon mode, and you have this upper mode which becomes plasmon-like again. And now we are at a density which is around here, and you see you have high reflectivity from here, then there comes a longitudinal mode, this gives this narrow dip, but immediately after it comes the transverse mode, the reflectivity goes up again, and then it decays gradually until you are here again at this longitudinal mode. And the quanta of this thing are quanta of the plasmon phonon mixed state. Yeah, that's the
Interaction is large, as I can see. Interaction is large.
Yeah, here.
Splitting is large.
Yeah. Now, this is, I think, the last example for plasmons. What happens with plasmons in a quantum well? And we saw before that the plasmon dispersion starts at the longitudinal frequency. If you have a quantum well, the dispersion starts already at k equals 0, even for the longitudinal mode. And this is very simple. If you have a bulk material, you have charged layers. And the electric field is constant, independent if the spacing or the wavelengths of the layers is like this or like that. In a quantum well, if you have a plasmon, you have charged lines. And if you go to longer wavelengths, the electric field gets weaker and weaker. And if you go to infinitely long wavelengths, the eigenfrequency goes to 0. And these are now, I think, from Raman scattering, the plasmon modes in a doped quantum well, and you see the dispersion relation here. Starts really at, for k equals 0 at frequency 0.
What's the difference between these two curves? What's the difference between these two curves?
The two samples. Sample 2, the thickness. This is 27 and this is 26, 24 nanometers. And yeah. And also maybe the doping level is different. So now I would really like to go back to the topic we had recently. Let me just check what I have here. Oops. Yeah, okay. So then we will switch this one off.
So this
yeah, this one is okay, yeah.
Okay.
Can I see it here? Or?
Oh, it's probably difficult. I will check.
Otherwise I have to
Just.
Then I would like you to close your eyes for a few seconds because I have to go very rapidly through the whole thing which we had yesterday, and we do not need to repeat it again. Gradually we should arrive. No, there's still the bikes that are missing, and now we are also here in the range of the quantum wells, and the first transparency is the density of states. We saw it already for an effective mass approximation in 3 dimensions, square root density of states, 2-dimensional step-like function, 1 over square root of a 0-dimensional delta-like functions. And now you can, if you have these two materials, you may have different alignments of the band gaps, and we concentrate at the beginning at least mainly on the so-called type 1 alignment, where the minimum of the conduction band, so this black thing here is the conduction band in material 1 and material 2, where the minimum of the conduction band and the maximum of the valence band occur in the same material. So you can confine electrons here and holes here in a plane which is perpendicular to the drawing, to the table plane here. There are type 2 and so on. Now you get quantized levels, and for infinitely high barriers, this would be the most simple one, you would get quantized levels here with a dispersion, a parabolic dispersion in the plane, and you can write down the quantization energy in this case, and you get this equation. Now, in reality, the barriers are not infinitely high. You have a barrier height of maybe several 10 or 100 millielectron volts, so you get only a finite number of quantized states, and you get a little bit of tunneling into the wave function, into the barrier for the electrons, and the same for the holes. And you get here a splitting here because the quantization energy depends on the mass. And if you have a heavy hole and a light hole, you get different quantized states for heavy hole and light hole. And then you can play around and produce, for example, a heavy hole exciton with an electron here and a hole here, or you can produce a light hole exciton with the electron still here, but the hole here in this quantized state, and so on. And this is a further aspect. If you make the barriers narrow, it's shown schematically here, then the quantized levels start to overlap a little bit in the barriers, and what happens if they overlap, you get a splitting, and this means you get even in the direction of the growth direction, perpendicular to the quantum wells, you get so-called mini bands, and they have also some dispersion here. This is the superlattice period. If you make the period shorter and shorter, you get first more and more quantization, the blue shift, and you get overlap and the opening of these mini-bands, and they have some influence on the density of states, which is not along a step-like, but it has such a little bit curvature. And we will see experimental results now. One important aspect for quantum wells is that you always have a certain amount of disorder. For example, if you grow a barrier of aluminium gallium arsenide and then you grow gallium arsenide well and another barrier, then you cannot avoid that you get fluctuations of the well width of at least one atomic layer, frequently more. And then you get localization, so maybe you localize a hole here or a hole here, and you can bind the electron to it, so you get localized states in quantum wells usually. This is only a few equations. This was the exciton energy for a bulk material where the exciton can move freely in 3 dimensions. If you restrict it to 2 dimensions, then you get this term for the binding energy main quantum number -1/2. This means ideally the binding energy would go up by a factor of 4. And you have, of course, only motion in the plane of the quantum well. And some for finite thicknesses you have some formula which extrapolates in between. And these are now calculated data, but they agree approximately with experiment. This would be for gallium arsenide, the exciton binding energy is for very large wells approximately 4 millielectron volt. It would go up to 4 times 4 millielectron volt, 16 millielectron volts for a strictly 2-dimensional system. In reality it goes up, but then it reaches the binding energy of gallium aluminium arsenide, because if the quantum well width goes to 0, the exciton resides in the barrier, and you have the binding energy, a barrier material. Now, examples. This is a gallium arsenide layer of 400 nanometer thickness, so this is for these purposes a bulk material. You have the 1s exciton, and you have then the absorption and the excitonic ionization continuum. Now 20 nanometers, you get now exciton states n equal 1, quantized level, heavy hole, light hole, n equal 2, heavy hole, light hole, and so on, n equal 3. If you make the quantum well narrower and narrower, the quantization energy shifts the whole thing to the blue. The splitting between light and heavy hole is also increasing. And so,
yes, can you return to previous slide?
The previous slide, yeah.
Yes. 1 nanometer.
This is theory.
Huh?
In theory, you can go to 1 nanometer and below. In experiment, it's difficult.
It's infinitely high probably variance.
The dashed line would be for an infinitely high barrier. If you make a quantum well with infinitely high barrier and you make it narrower and narrower and you go to thickness 0, then the binding energy increases by a factor of 4. In gallium arsenide it is 4 millielectron volts, and here you reach 16 millielectron.
But what is the thickness of quantum well which corresponds to the highest exciton binding energy?
This would be something like here, 10
Right
angstrom,
here.
10, 5 to 10
It's
angstrom.
few.
A few atomic
angstrom.
layers. Yeah.
But
I
these,
think it's 30.
these approximated calculations, of course.
Yeah. I do not know
we will show you more exact calculations of this system.
It would. What I know, what is correct, that you reach approximately maximum binding energies of the range of 9
But I
millimeters.
think
It strongly depends on the model.
Even said.
that it's
Yes.
not
We
right.
will
Okay.
discuss
Okay.
after lesson.
Quantum
Okay.
well thickness, I think it's not right.
You think
No,
you need?
not correct.
You would expect the maximum a little bit more to
Yes,
larger.
yes.
To larger
About
models.
2 or 3 nanometers.
Okay,
Yes.
okay, thank you. So next time I will take care about this.
Uh,
Okay, these were experimental. Sure.
Maybe it was the previous slide. What is really the problem is how can we distinguish this main quantum number of exciton,
Yeah.
binding energy, and this quantum confined energies?
Yeah. The main quantum number of the exciton, you do not see much in these quantum wells. I do not know, possibly this animal here could be a higher main quantum number.
From quantum confinement.
No, from poor quantum number.
For exciton
These quantum numbers here are the quantization. So this was
one S state probably.
one is state for the
And this-
first quantized
Yes,
heavy
yes.
and light hole. One is exciton state for the second quantized. Electron
and one for the and
For the Bohr quantum number is 1.
okay.
Also here 1, also here 1. This is, you see, essentially only the ground states. The higher states have very relatively weak oscillator strength.
But probably that small piece.
This could be possibly
2S.
a Bohr quantum number 2 for this first
Yes,
quantized
For
level.
exciton, yeah?
Yeah.
For exciton, internal structure.
Okay.
Now this is something to show you, I said some disorder due to Welwitz fluctuations, and this shows you simply 2 samples of different quality. This is, they are approximately equal concerning Welwitz and concentrations and so on, but you see here the heavy hole n equal 1, exciton and absorption, the light hole, and you see the luminescence, which shows hardly any shift compared to the absorption, and possibly you see here even some bound exciton states. If you have more Welwitz fluctuations and more localization effects, then you get a shift between the absorption and the emission seen here. So just by measuring absorption and luminescence, you could say the lower sample is not so good quality concerning the flatness of the quantum wells than the upper one. And this is a comparison between a macroscopic luminescence spectrum, this flat curve here, and then by maybe confocal microscopy or something like this, you can investigate a tiny spot, and if you do so, you see here many spikes, and these spikes are not noise, these are individual localized excitons localized in the various Welwitz fluctuations. We had, in the last lecture, we heard about excitonic molecules, and excitonic molecules exist also in quantum wells, and this is a sample maybe not too high quality. The absorption, the luminescence, you see there is a certain shift, and with increasing pump power you get a new band growing more than linear with a slope 1.4, and the authors attributed to the decay of an excitonic molecule, such an M band. And what you can also, one step further, the next aspect which we had was the transition to an electron hole plasma, and such an electron hole plasma exists also in quantum wells, and you see here multiple quantum wells, the absorption spectrum, first quantized level light and heavy hole, second quantized level, and then we pump harder and harder, up to 6 megawatt per square centimeter. This was, I think, nanosecond pulses, and you see the excitons disappear, and you get negative absorptions. This means optical gain, and this means the band gap comes down, it's renormalized to a value around here, and the chemical potential is approximately here. These modulations here, these are Fabry-Perot modes when the sample becomes transparent, and you can deduce from a line shape fit the renormalization of the band gap and the chemical potential mu, and you see here the renormalization fits quite well with theoretical models, and this is a range where you have optical amplification or gain, so there you can build quantum ballets in this range.
Now, how do you measure the absorption spectra?
Which one?
How do you measure the absorption spectra in this?
There are two ways. Either you have to selectively remove by etching the substrate, or you measure photoluminescence excitation spectra and hope that it agrees with the absorption spectrum.
You believe that it is?
No, not always. Okay. So this brings us to the end of part one. Then can we switch back again to the second part, where we continue now a little bit with quantum wells. So, yeah, okay. This is good if you are here.
That's okay.
Okay. Okay, good. So this is what we do here. This is now, I said we are mainly talking about type 1 superlattices or quantum wells. This is now a little bit strange phenomenon which we observed when we were growing strained cadmium sulfide, cadmium selenide superlattices. They have different lattice constant, so if you grow thin layers, one is compressed and the other is a little bit expanded. This is the first part of the story. The second part of the story is they show the piezo effect. So if you strain some, you get piezoelectric fields, and these piezo fields tilt the bands. So this would be, in principle, the valence band edge. This is the cadmium selenide, the cadmium sulfide, but it is tilted alternatively by the piezo field. And this means you have the quantized hole levels here. This is the envelope of the wave function, or here. And for the electrons you have the opposite behavior, so you have the electrons confined here. So in a certain sense you have a spatially indirect transition. If you pump hard enough, you create a lot of electrons and holes, and these electrons and holes screen the piezo field. So if you would screen it completely, you would come here to such a rectangular shape. If it's not completely screened, you get something in between. But you see here that now the overlap of the whole wave function and of the electron wave function is much bigger. And what we did, we excited by a short pulse, and then we measured the temporally and spectrally resolved the decay of the luminescence. And at the beginning, we had relatively highly filled bands. We get a broad spectrum and a relatively fast decay at the beginning. Then this piezo field recovers again. The transition probability gets smaller, the decay gets slower. You see here this scale is strongly nonlinear, and we move back to the situation. And these are calculated as a function of time, the various quantized levels which we have here, and together with the experimental data points.
But decay should be strongly nonlinear. Non-exponential.
Non-exponential, yeah. Because the transition probability depends on the density, and the density decreases. This is exactly the point.
How about the spontaneous polarization? Spontaneous polarization is when you have a similar structure but without strain.
Yeah.
This Wurtzite type structure.
I do not know if you have a macroscopic polarization, because in one layer you have the electric field like this, and the other opposite direction, and then like this. So the sum may be close to zero.
But this effect, piezo effect, should strongly depend on orientation of substrate.
Yeah. So you can, in principle, you may have orientations where you have no piezo effect.
Yes.
But we draw usually crystallographic CXs like this, and then you have this. So this is another way to get a spatially indirect transition. Usually one grows gallium arsenide, and aluminium gallium arsenide with an aluminium content that is still a direct gap semiconductor. Now this is pure aluminium arsenide, and now the valence band edge at the gamma point is this one here, and you get quantized level here in the gallium arsenide. In the X point minimum is here, it is higher in gallium arsenide but lower here in aluminium arsenide. And depending on the width of these wells and barriers, you can either come to a situation where this is the lowest state or this is the lowest state, and either you have a direct or a spatially indirect transition. And this is a relatively long period superlattice here in the luminescence spectrum, and here not the absorption spectrum but the photoluminescence excitation spectrum, which we hope coincides approximately with the absorption, almost coincide. This is a much narrower situation, and here you have really an energetic distance between the two, and this absorption here is very weak. This means you get here only a weak absorption for the spatially indirect transition, and the real absorption starts only here. But the luminescence, the electrons drop down here, the luminescence comes from this at low temperature from this indirect transition. Another twist of the polaritron story is the so-called cavity polaritons. First, what is a cavity? In simplest case, a cavity consists of two highly reflecting plane parallel mirrors, and if you shine light on it, usually all the light is reflected, except that an integer number of half waves, in this case 2 half waves, fit into this resonator. Then you get a high field amplitude in the resonator and a transmission close to 1, otherwise the reflectivity is close to 1. Now, these cavity polaritron modes have also a dispersion, and what is important here is the parallel component of the k vector. The normal component for these modes is fixed. It must be an integer multiple of pi over the given geometrical thickness, and if you tilt the angle of incidence like this, then these modes shift to the blue spectral part. This is just the light cone and the intersection with k perpendicular equal constant. This gives a parabola, and in the minimum you can approximate it by a parabola. Now, you can grow in this cavity a few quantum wells. And then you have again such a system which I evidently like. You have two coupled states. This would be the dispersion of the empty cavity mode. This would be the dispersion of the exciton resonance, and you grow these quantum wells in the cavity here at positions of the antinode of the standing wave. They couple to each other, and you get a splitting, you get again this avoided crossing here. And always take photos. I would have a simpler solution. I just let you a copy. You can have from the computer a copy of my transparencies. Yeah, this is easier. This is now calculated curves without coupling, and the dash dotted lines with coupling, depending on the detuning between the bottom of this cavity polariton and the exciton resonance, and you see this phenomenon, and you see here a measured luminescence spectrum where you can see nicely this upper cavity polariton branch, and here's the lower one. Now, a few words for examples of reduced dimensionality. And from second to quasi one dimensions, there are various possibilities. Either you take a quantum well and you etch a ridge, then you have a one-dimensional system. You can grow in a groove here, and you get a quantum well here, a quantum well here, and here you accumulate a little bit more material, and actually the electronic states in these quantum wells here and here are higher than here in the bottom of this groove, so you get a confinement of the electrons in this V groove. You could do the same with a ridge, or you can grow a quantum well, you cleave the sample, you grow perpendicular to it another quantum well and a barrier, then you have these T-shaped quantum wires. Density of states we had already. Now this is such a V-groove example, and this is an overview of the luminescence, and as I told you, you see the luminescence from the quantum well on the surface, from the quantum well in the groove, and strange enough at the lowest energy the quantum wire, where you have a thicker material and the electron and holes cannot escape sidewards. And if you increase the pump power, you see that you fill the first quantized level, then you start to occupy the second quantized level in the wire, the third quantized level. So you can play around if you want with these excitons in the quantum wires. Next step, quantum dots. How can you produce quantum dots? Either you go again to lithography and you produce such pancake-shaped dots. Yeah.
And back to the quantum wire. What is really the status of calculation of such kind of system?
I guess it is correct. I guess that these lines here, I guess,
it's possible to calculate really the values.
It is not trivial because you have a little bit strange potential from this quantum well. So you must go to some numerical techniques, but I think it can be done by finite element methods or something like this. So either by lithography you can produce such pancake-shaped dots. You can produce almost spherical quantum dots in a matrix. This can be glass. This can be an organic material in which you precipitate these things. You can grow quantum wells on a substrate if you have a certain fit between the lattice constants. Then you can grow a wetting layer, and if you grow more, you get such small hills or islands on this wetting layer, which act as quantum wells. The problem is if you put a cap layer on top of it, usually due to segregation and interdiffusion, you no longer have such beautiful quantum pyramids, but a little bit of mixture. Sometimes you get still a relatively good quantum pyramids. And then you expect, of course, that the exciton binding energy increases the more you reduce the dimensionality. And these are now measured and calculated curves for quantum wires, deep-edged or with a modulated barrier. So you see here it goes up for quantum dots, also deep-edged and modulated barrier, and you see it can go relatively high up. I do not know what the material is, gallium arsenide or indium arsenide. I would guess one of these two. These are calculated absorption spectra for quantum dots of cadmium sulfide in a glass matrix. And you have with these quantum dots always the problem that you have a certain size distribution. So you have an inhomogeneous broadening. And this is just from Stefan Kocher calculation for dots. I do not know, the size is constant for all, but the size distribution is changing, and of course the broader the size distribution, the more are these absorption features washed out. And these are again the transition between the first quantized level, second and so on. These are measurements now not for cadmium sulfide, but for cadmium selenide quantum dots, I think in glass matrix of various sizes here, and you see here the various calculated quantized levels. The height of these lines gives the oscillator strength, and you see that there is reasonable agreement between here the stronger features in absorption and the calculated levels. And what you could also do, you could plot now the splitting of maybe this first and the second levels as a function of the position of the first level, and this is shown here. First over the 1 over the radius squared is the first level. You see here the increasing quantization. When you go to smaller radii, this is 1 over the radius squared, and then the energetic distance from the first level to higher levels as a function of the position of the first level. So this is also relatively well understood. And concerning the size distribution, you have also the problem if you have a size distribution. You get a broad absorption or luminescence feature. If you are able to look at only one of these quantum dots, you get much narrower lines. Biexcitons in quantum dots. Do they exist? Yes. This is copper bromide in glass matrix. And we observed when we were increasing the pump power, here a peak and then another one coming up with higher intensities. And what we plotted here is again as a function over the radius, 1 over the radius squared. the position of the high energy and of the low energy peak, and you see the high energy peak converges to the exciton energy in bulk samples, and the low energy peak tends to converge to the bi-exciton energy in bulk. So we think this is due to a bi-exciton in the quantum dot, and the binding energy, which we can deduce here from this difference, corresponds also reasonably well to theory. So with these examples I want to stop the discussion of these optical properties, and I want to say a little bit about time-resolved spectroscopy. And we first have to introduce the various time constants. We have here our exciton states, or if you want polariton states here, and we excite with a short pulse, maybe here into the continuum. And in the first moment, the polarization which is connected with this excitation here oscillates in phase with the driving laser field. And then you possibly may undergo a scattering process and you lose this phase coherence, and the characteristic time constant here is called T2 time, or transverse dephasing time, or phase relaxation time, or decoherence time. This is approximately the same. What may happen then is that this electron-hole pair relaxes down through the continuum, maybe by emission of optic phonons, acoustic phonons, and comes down here at the bottom. This is intra-band relaxation time. It's also sometimes called T3. And finally it disappears, so it has a certain lifetime, T1. Could be radiative, or in most cases non-radiative recombination. There's some relations between these lifetimes, because if in the recombination process the coherence is finally lost, and this gives here this relation here, this factor 2 comes, that the population goes with the amplitude squared. Now, how can we measure first the dephasing time? And there is one rather, okay, in principle you can measure it from the absorption spectrum if you know that it's only homogeneously broadened. This you usually do not know. So you must take other possibilities, and one is so-called four-wave mixing. What you are doing, you send a short laser pulse in the sample, which produces some polarization, but this one comes first. With a certain time delay, you send a second laser pulse, which also produces a polarization, and the polarization, the leftover from the first pulse, interferes with the polarization produced by the second pulse. You get a modulation of the polarization, you get a diffraction grating, and you get a diffractive order. Now, if this transition is really homogeneously broadened, you have the situation, the first pulse comes, produces a polarization which decays, the second pulse comes, produces a polarization which decays and which interferes with the leftover. You get a diffracted intensity which goes maybe like the product of the two. And if you vary the time delay between the two pulses and measure the decay of the diffractive order, you can deduce the phase relaxation time. If you have inhomogeneous broadening, and this is almost always the case, if you have inhomogeneous broadening, you run into the following problem. You excite with the first pulse transitions. Every transition has a little bit different frequency. So they oscillate, and with time they run out of phase with each other. They do not lose phase coherence to the driving pulse, but among each other they lose the phase. This means the polarization decays here due to this inhomogeneous broadening. Then comes the next pulse, and strangely enough, after twice the delay time, you get a photon echo. And this photon echo can be calculated using optical Bloch equation or semiconductor Bloch equations. I want to explain it here in a very simple way. It's a type of phase reversal. Assume we have our oscillators here. The first pulse says start, and they start running here. And everybody has a little bit different phase frequency, so one runs a little bit faster, the other one slower. Some undergo a scattering process. Even if they continue to run, they are out of phase, they are out of the game. Now comes the second pulse, and the second pulse says, turn around. And then they turn around and run back again, and you see the one which is the fastest has the longest distance to go, but when he goes back, he also is the fastest. And so after twice the delay times, they are all again here, just showing in the opposite phase, and this describes you the radiation of this photon echo. And these are now examples. The decay of the photon echo in cadmium selenide in the exciton resonance measured then in a reflection, or at a exciton bi-exciton transition measured in transmission. And you see with increasing pump power the decay can get faster. And what is plotted here is now a function of the exciton density, the dephasing rate. So this is just the inverse of the dephasing time. And you see here at low density the dephasing time can be relatively long. In this case it's 40 picoseconds. It's a little bit surprising for me. I would have expected something closer to 10 picoseconds or so. But if you increase the density of excitons, they scatter, and the dephasing rate increases. This means the dephasing time.
But what is the physical reason for? What is the physical reason for
scattering between excitons? If
exciton,
you have an exciton, it has a polarization. If it hits another exciton, the phase coherence is lost. It's an inelastic scattering process. The phase coherence is lost. Now, if you do not go to a free exciton, but if you go to a bound exciton complex, here's the A0X, the exciton bound to a neutral acceptor. Here you see really the photon echo, the scattered light from the first pulse, the scattered light of the second pulse, and the photon echo. And for these localized states you have much longer dephasing times. You see here a dephasing time T2 of more than 500 picoseconds, so these dephasing times are longer. Simply because the exciton is localized, it's a defect. It cannot move around, it cannot scatter with another localized defect, and so the dephasing time is longer. If you go to higher temperatures, the dephasing time goes down. This is due to scattering with acoustic phonons and with optic phonons.
Oh, please.
Yeah.
You speak about the resonance creation of bound excitons.
Yes. Yeah. No, if you create some higher energies, first relax down, and then the phase coherence is lost. And the same holds if you go to localized exciton states. We saw such a picture already the day before yesterday, that these are also for the localized states dephasing times which come into the nanosecond range of velocity.
so large? Nanoseconds? So
Hmm?
large?
Nanosecond, it's large, yeah. We were really surprised. You must be careful if you do the experiments. We measured the dephasing time as a function or depending on the duration of the laser pulse. This was a 10 picosecond laser pulse, and you see a very slow decay of the signal. This is 1 nanosecond here. This was a 5 picosecond pulse, the decay is already faster. This is a 1 picosecond pulse, the decay is even faster. These are only 15 picoseconds. And this is a 0.1 picosecond pulse, and the decay is almost instantaneous. Our explanation is the following. We have here the localized states, we have a mobility edge and extended states. And if we have a narrow laser and we excite, and this means a long, temporarily long laser, and if we excite directly in the localized states, we measure these long times. If you make the laser pulse shorter and shorter, it will become spectrally broader and broader, and we excite also extended states, and they scatter with the localized states, and then the phase coherence is done.
Well, but
Yeah.
you show us 4 different samples, not only 4 different conditions, let's say.
Yeah, it's not 4 different, maybe it's in reality 2 different samples. I guess this and this one are the same. This depends where we have the lasers, because these short pulse lasers, at that time you did not have every frequency you wanted. This is now an example for intraband relaxation. This is a quantum well and the change in the transmission, the differential transmission. And the pump pulse is situated here, and this would be the positions of the excitons. And the pump pulse has a certain duration, so you have a time delay minus 100 picoseconds 50, 0. And this, during the maximum of the pump pulse, you get here some bleaching in the band-to-band transition region and a little bit of bleaching in the exciton resonances. And with time, this population here is trickling down, relaxing down to the exciton resonances, and then you have here a lot of bleaching and almost no more bleaching here. So you could determine that the time it takes from for the electron hole pairs to relax from here to the exciton states is of the order of 100 picoseconds. This is another example for a intraband relaxation. We were growing zinc selenide, zinc sulfide selenide superlattices. This is a zero phonoluminescence of the exciton in the quantum world. This is a dispersion in the plane. And we excite one or possibly two LO phonon energies above this lowest dispersion curve. And then we have a fast relaxation by LO phonon emission coming maybe somewhere here. And then it trickles down and we see it here in the zero phonoluminescence. But we can investigate this whole evolution of the population here by looking at the recombination under emission of a phonon here, because with an optical phonon we can scatter here. If the exciton is here, you do not see it in luminescence because K conservation forbids it, but with the LO phonon you can come here, you can see it here and so on. And this is now the temporal evolution. We excite two LO phonon energies above this energy with a dashed line, and we see relatively rapidly we get a population here, which we observe in this peak, and then with time they relax down and they end up in this range, and then we get this luminescence here. And here we had, I think, 8 millielectron volts excess energy above the exciton, minus 2 LU, and here we had 15 millielectron excess energy, and you see really how these excitons relax down either through the 8 millielectron volts or through the 15 millielectron volts.
Excuse me, is it luminescence?
This is luminescence, yeah. These are luminescence spectra.
How did you observe luminescence exactly at the
time resolved? This is time resolved, so this was zero.
Spectrally, minus 2 energy of LO phonons, yes?
Yeah, we excite 2 LO phonons above this state here.
From this point.
Yeah, and then it relaxes by emission of 2 LO phonons, it comes to this state. And we see the population in this state here in the LO phonon recombination. And we measured the spectra with a streak camera, so we have time resolution and spectral resolution. And then you see how they trickle down here in the LO phonon luminescence.
But your population at minus 15 picosecond already present. Minus 15 picoseconds already present this population.
Minus 15 picoseconds, this is where our pulse starts already at 0 picosecond, it has this maximum, and then it is, if you wanted a plus 15 picoseconds, it is gone. So this is during the excitation pulse, was maybe 20 picoseconds, and then it's a short pulse, yeah, and then it relaxes down. You see the population here disappears because the exciton relaxes down here.
Probably you have
and
pulse short, but time resolution of streak camera plus spectrometer is not short.
Which one?
Spectral resolution of your optical setup, streak camera plus spectrometer, is not small.
It is good. You see here how narrow the lines are, which we can observe. So the spectral resolution must be better than this. As a time resolution, we had a streak camera where we could choose the time resolution. So here we had maybe time resolution of
20 picoseconds.
20 picoseconds, something like this. Now the last time constant is of course decay time, and you find frequently papers where the luminescence decay time is associated with the radiative decay time, which is in most cases an error. And what we measured here is we just measured for various samples as a function of temperature the luminescence decay time, and in some cases we had hardly any variation with temperature, or we had stronger variations with temperature. We measured also the luminescence yield, and we know that it is considerably below 1. And we even measured the time resolved, the luminescence intensity. And these are two different experiments. In one, here we excite resonantly in the heavy hole exciton, and at weak excitation we see a relatively fast decay of the luminescence. This is simply that the excitons are trapped into some defects, we fall in some defects. If we pump harder, then we have at the beginning it's also this rapid decay, but once the defects are saturated, then maybe we see something like the exponential luminescence decay. And if we pump even harder, then we heat the exciton gas. We also saturate first the defect states, and then the exciton gas has to cool a little bit down, and only here we observe really something like exponential decay. And here we excited at higher energy in the heavy hole exciton resonance, so it takes some time for the exciton to relax down. We excited in the light hole to the heavy hole, and you see we get a different behavior, and with a few reasonable assumptions we were able to model this 1', 2' is here 1 and 2, and 5', 6' are these two. We are able to model this decay, but you must be careful. It is very difficult to observe a simple one exponential decay and to say this is a decay times a decay times 1 nanosecond or 5 nanoseconds. You have in most cases you have no
What are the physical origin of this long lifetime of excitons?
Can you go back? These are luminescence decay times in the range of nanoseconds.
And what are the origin of this? Why so long?
Why? But you would expect it to be much shorter? Or what?
10 picosecond.
No. I think there's a transition matrix element for gallium arsenide does not give you much shorter time.
Typically we directly observe by pump probe technique 10 picosecond or smaller. Radiative decay time at low temperature, of course.
Yeah, at low temperature possibly we agree. You see here this is 1 pic. Oh, sorry, no, we do not agree. This is 1000 picoseconds, so this is maybe 100 picoseconds decay time. But this is what we also...
It might be localized exciton, not free exciton.
It could, at low temperatures it could be localized, but if you go to higher temperatures, the lifetimes tend to get even longer.
Yes, but these non-radiative excitons with large kinetic energy, yes? Which are not radiative due to a large wave vector, much larger than wave vector of light.
Okay, yeah. And it takes some time to cool down, and only the ones which are cooled down you see in luminescence. This explains the increase with temperature. Yeah. So I come to the how much time is it? Oh, okay. 15 minutes for Bose-Einstein condensation. Okay, what is a Bose-Einstein condensation? You would expect you create a population of excitons or pi-excitons or what else, and if you go at a constant temperature above a critical density, or if you go at a constant density below a critical temperature, you get a spontaneous population of one state of generally of the ground state. And the relation between critical temperature and density is given here, and excitons are much lighter than maybe rubidium atoms, and the density can be increased by optical pumping. So people expected it should be very easy to observe a Bose-Einstein condensation of excitons in semiconductors. And then, of course, people started to investigate. These are some authors, and it was sometimes for a time everybody who saw a narrow line, or at least many people, when they saw a narrow line, they shouted Bose-Einstein condensation, and it turned out to be wrong. Now, if you have a polariton, if the exciton couples to the radiation field, it is difficult to say what a condensation means. It condenses to the ground state. Okay, so this is, you should go to a system where you have an exciton which does not couple to the light field, then it's difficult to observe it. People tried it in indirect gap semiconductors like silicon and germanium, they always run into an electron hole plasma. They tried it in copper oxide with only limited success. They put inhomogeneous strain on the copper oxide to produce a minimum and to produce a potential trap. And 3 days ago I received an email from Heinrich Stolz in Rostock. He's working on this system. He told me, maybe most probably we have it, but they want to do some more measurements. So there are some reasons. There can be Auger processes. There's a discussion that in copper oxide also biexcitons may be formed which decay non-radiatively and so on and so on. To make the long story short, in bulk samples there is, maybe apart from this very recent data from Heinrich Stolz, no excitonic Bose-Einstein condensation observed. And I'm not a theoretician, I'm a pedestrian experimental physicist, and I try to understand why. And this was an idea. This is a function of the density, normalized temperature, what happens in the electron hole pair system. Of course, we can produce excitons at low density, this is fine, but there we do not expect a Bose-Einstein condensation. This is a limit to observe a Bose-Einstein condensation, so here Bose-Einstein condensation should occur. On the other hand, we know that an electron hole plasma can be formed, and we need a long lifetime for both for the Bose-Einstein condensation to develop, and we need a long lifetime for the phase separation in the plasma to develop. This is a phase diagram for the electron hole plasma. So if you create excitons maybe at a density here, where you should observe a Bose-Einstein condensation, possibly you get a phase separation in a liquid and a low density gas. And then theoreticians tell us, well, if this quantity is above 1/8 pi, excitons are no longer good bosons. If you write down the commutation operators for excitons, they follow Bose, what you expect for bosons, but with a correction term, and the correction term depends on the density. So the higher the density, the less boson-like are the excitons. Yeah, and if I do not take this too serious, this is a mod density in Thomas Fermi approximation and the bi-Hügel approximation, but there is only something left which is just in the middle of the coexistence region, so maybe this is the reason why it's so difficult to observe.
So, sorry, this very small area of your diagram for Bose-Einstein condensation. Only for Bose-Einstein.
Yeah, here if you take this model serious, and I'm not sure if it's serious, then you could expect a Bose-Einstein condensation here, but then you are possibly in the range where you get a phase separation in liquid and exciton gas. Now then people started to work on quantum wells, and one trick was really a good trick. They grow 2 quantum wells in a pin structure, applied an electric field. This tilts this structure, and then they have the electron sitting here, the hole sitting here. This means the dipole moments of all excitons are parallel. You get a weak repulsive interaction. You cannot get molecules, you cannot get electron hole plasma. And then both 2 groups, one of Butov and one of Snook, they observed luminescence from the excitation spot, and then they observed nothing and only then a ring of luminescence. And their idea was, it was letters to, in Nature, we produce excitons, they undergo a Bose condensation, they become superfluid, they expand with velocity of sound, and only where they stop to expand, we observe luminescence here. Okay. Snook stated later that this ring structure has nothing to do with the superfluid expansion, but he gave the following argument. He said the electrons may tunnel out here because they are light particles. The holes cannot tunnel out because they are much heavier, so there is a puddle of holes left, and just at the border of this puddle of holes, when an electron comes in, he gets the luminescence. And recently Heinrich Stolz also told me that it is more or less nonsense with this ring to attribute it to a Bose-Einstein condensation. The system which is, to my understanding, closest and maybe really a Bose-Einstein condensation are now cavity polaritons. And the first successful attempt was with cadmium telluride quantum wells in these cavities. And they excited the polaritons with some excess energy, so they have to relax down to this lower minimum. Maybe I can go for a second just back to what we had. No, sorry, the cavity polaritons are in the other top, so I will not go there. They relax down and then they get a luminescence, and the luminescence is a function of angle. This means of a parallel component of wave vector reproduces the lower part of the dispersion of these cavity polaritons. Here would be the upper branch. And now if they pump harder and harder, you could expect that the system gets hotter or something like this. So it expands more in K-space, but actually it was condensed more and more in K-space. This is shown here with this color and here. And so that now really they condense here. And this could really be true. This is work from the group of Le Sidang. And then later on other colleagues, in connection with Forte and others, they measured even another effect in a Bose-Einstein condensate. You expect a mode which has a linear dispersion. Now, if this cavity polariton here has a parabolic dispersion and at low density you see it, but if they increased the density, they saw that something like a linear mode here develops, and they attributed it to this Bogoliubov mode, I think is the name. And so I think that really a Bose-Einstein condensation has been observed for these cavity polaritons, but this is, with maybe recent results of copper oxide, the only system where I would really speak about a Bose-Einstein condensation. What people did before, they shine a laser on the sample and populate a state, and then they find out that excitons or polaritons are scattered preferentially into this state. But this is not a Bose-Einstein condensation in thermodynamic equilibrium. If you from outside produce the condensate and see, this proves the Bose character of the particles, but it's not a Bose-Einstein condensation. Yeah, there are still some things to do to prove, for example, coherence and phenomena and so on. But in this cavity polariton system, I think Bose-Einstein condensation has been observed. This finishes my part 2. I thank you for your attention and ask your further questions.
Please, questions?
Maybe not questions, but some comments.
Yeah.
If we separate the Bose-Einstein condensation process and Bose-Einstein state as a result of this process, so we could create excitons just in the final Bose state, because we create it by light. We can prepare for some sample, we can prepare light with given energy, with a given transverse momentum, for example, and just have already Bose-Einstein condensate state. Of course, we are limited to study only the decay of this state. We can create it by light, not by spontaneous condensation.
These are two questions. As far as I understood your idea, you have somewhere the polariton or exciton dispersion, you populate this state.
Yes.
Okay. And
then I can
then
observe.
they are scattered out of this state, I would expect.
Yes.
They would thermalize.
But we can carefully study the decay of this state.
Yeah.
For example, decay rate as a function of excitation density, and see a difference some between a coherent collective state and some.
You can do all of these things, but you must. I would still not call it a Bose-Einstein condensation in thermodynamic equilibrium. You put it from outside into the system. This is the difference. And another aspect is laser emission. This is with all these polaritons, you populate a state, but you can, with a laser, if it starts lasing at some frequency, you also coherently populate a state. laser emission. So what is the difference between a Bose-Einstein condensation somewhere on the polariton dispersion and laser emission? So these are difficult questions. I think we agree on this topic.
Simple problem with linear dispersion, for example, not possible to check Bogolyubov linear dispersion with
But two-dimensional Bose condensation is impossible to my knowledge. Two-dimensional Bose-Einstein condensation is impossible.
It's a Staulis transition, I think, something like this. Could it be correct answer?
It is some modification of this phase transition, yes?
But in the literature, it's usually strong theoreticians distinguish between dimensionality, but in many cases they just say it's also a question if you produce a trap where this whole thing appears, or if you have really infinite space and so on.
If I produce three-dimensional trap, no question. But
this is an analog to the rubidium atoms, which are also put into a trap.
Rubidium atoms, no question. With cavity polaritons, this is two-dimensional system.
Almost quasi two-dimensional. Okay.
More questions? Thank you again.
Tomorrow you will hear not everything about zinc oxide, not a lot of it.